Hello, everybody. This is Ming from Momentum Learning. In this session, I'm going to review the 3 questions in the bronze level contest in the past round, January 2023. Question 1, that's cow leaders. Question 2, that's air conditioning 2. And question 3, that's moo operations. Let's start from question 1. In this question, we're given n cows, n can go to 10.5. So as we mentioned many times, whenever n can go to 10.5, there must be an easy way. In general, the input size n for bronze level contests should be less than in the magnitude of 10.3 thousands, not in the 10.5 hundreds of thousands. So whenever n goes to 10.5, there must be an easy way. So you need to find out that shortcut or that sharp observation. So here we're given n cows. The type of each cow is also specified in the input. So here there are 4 cows. The types either G or H are specified here. And also we're given the number E. This number E is an integer. So for each cow I, it will visit from position I to position EI inclusive. So here for cow 1, it will visit position 1 and 2. Cow 2 will visit positions 2, 3, 4. Cow 3 will just stay at position 3. Cow 4 will stay at position 4. And a cow is said to be a leader. It must satisfy 2 conditions. Either this cow will visit all the cows of the same kind, or cows in the kind. So here cow 2 is such a leader, right? Because cow 2 visits positions 2, 3, 4. So it does cover the other cow 4, which at position 3. So cow 2 can be a leader. Or if a cow visits the leader of the other kind, So here cow 1 visits positions 1 and 2. Cow 2 is at position 2. So this cow 1 visits the leader of the other type. So cow 1 can also be a leader. Of course, it can be both. For example, right, if cow 1 visits 1 through 4, then cow 1 visits all the cows of the same kind of G, but cow 1 also visits the leader of the type H. Either this condition or the other condition or both can put a cow as a leader. Now we're going to ask to answer the question, what is the number of the possible pairs of the leaders? Clearly, we cannot run the brute force idea, try all the combinations. So for the cow I here and for cow J, we're going to see, hey, can you both be the leaders? If you can, we're going to increase count by 1. But if you do this brute force way, then run a loop of 2 layers. I goes from 1 through n. J would go from I plus 1 through n here. So clearly, this is a loop of n layers in the outside and roughly, or an average n over 2 iterations in the inner layer. So that will give us n squared over 2 iterations. But when n goes to 10.5, this number is too big. Right? If n is 10.5, n squared is 1010 divided by 2, that's 5 billion. This number is big than our threshold, 10.9. If the number of iterations or the calculations, if it's big than a billion, then very likely you're going to run out of time and you're going to receive that TLE, the red box. So we cannot do this. Notice here, so here this is the hint, right? How can we find a shortcut, the sharp observation? So if you say, right, cow I and cow J, since cow I will only visit from I to the end, forward, cow J would also visit J from the end. It's never impossible. Cow I visits J and J visits I. Right? So the 2 numbers, suppose I is less than J. I can visit J because J is bigger, right, going forward, but J will never visit I, since J will only also visit forward. You don't have these 2 forming a cycle. So we can think the scenarios. The scenario, we can do this one here. One time, say G leaders will visit all the G's, so all H's, but G will visit H leader. The H leader will visit all the H cows. The G leader will just visit H leader. So in this case, right, this G has to come before the H leader, right? Must be this one. So this is the H leader will visit all the H cows, and this G leader must stay before this H leader. So it has the chance to visit the H leader, right? Cannot be after the H leader. And here for this H leader has to be the first one. Again, the same principle, because if you have H here, right, it's impossible to reach the leader H that is on the left side. So the H leader must be the first H in the lineup. And this G does not have to visit all other Gs, but if it visits this H leader, then that's fine. That's type 1. Type 2 is, well, just opposite by symmetry. G leader will visit all the G cows, but the H leader will visit the G leader. So it would be similar to this one. So all the G cows here, that's the G leader. And then the H cow does not have to be visiting all the H's. Could it be one H here? Could it be another H here? As long as this one does visit this G leader, then this can also be the leader of the H cows. Okay, and then there is another category. Then G leader can visits all the G cows. H leader will visit all the H cows. So we're going to avoid doing the overlap here. For example, right, this is the H leader. It's possible this H leader will also visit the G leader. So we're going to make sure they will be destroyed. So H cows will just visit all the H positions. G leader will visit all the G cows, and then they do not. So this H leader does not cover this G leader. So the EI must stay before this leader position of the G cow. And of course, you can do the other way. So G would stay in front of it, and then H would do appear all at the second half. Again, this G leader, right, can only visit some place right before the first H cow. Okay, you may have an H cow here, that's fine, as long as this one is not the leader. If this one is not the lead, right? For example, this one does not cover all the H cows, that's fine. So I'm going to say 8 G cows will cover all the G cows, H leader and G leader covers all the G cows, H leader covers all the H cows. Then these 3 cases will cover all the possibilities for the pairs of the leaders. So let's take a look at the code here. The cow leaders, and that's number of the cows. We're going to read the type of the n cows. So this is a string, and we're going to convert into an array of characters. What is this A here? Oh, that's the coverage. For each cow, how far it will visit from I to the AI here. So we're going to go read this one from the input, that's fine. But we're going to define these variables. So the first G position, the first cow H, and then the last G cow, the last H cow, and then answer is, of course, the answer we're going to report the number of possible pairs of the leaders. Reading the coverage, the visit of each cow, and we're going to make it 0-based rather than 1 indexed, because here we're going to do cow from 0 through n-1, so 0 indexed. And we're going to identify or find out the quantities, first G, first H, last G, last H. So here, if this position I is a G cow and first G is -1, that means we have not seen a G cow yet, then this is the first position of G cow. The same thing, if this one is H and we have not seen H before, then this is the location of the first location of a cow H. And then we're going to always update. If we see the G here, then the latest G is at a position I. The same thing, latest H is at a position I, if this is cow H. So after this loop, we have these 4 quantities specified. Now we're going to check the 3 scenarios. Scenario 1, if G leader visits all the G cows, but H leader only visited the G leader. So here, if the coverage of the leader, G leader here, it's bigger than or equal to the last G cow. That means, right, this cow G is indeed covering all the G cows. So this cow G is a leader. And then we're going to, for all the cow H, that is before the location of the first G, it has to be from the first H count, right? If you have a, well, has to come from the first H count here, and then right before FG here. If this position I is a count H, and also the coverage of this count I is big than or equal to the FG, the location of the first G count, then this is a pair, right? This count G plus, in addition, we're paired with this count H. Okay, that's exactly what we specified here. The second scenario is by symmetry. So count H, the leader covers the last count H here. So this is the leader, must be the first one. It can be paired with every G that is on the left side of the location of first count H or the H leader. And also this count G does cover the position of the H leader, then they can be paired. So we're going to increase answer by 1. Now we're going to do the third scenario. H leaders covers all the H cows. G leaders cover all the G cows. And then there is no overlap between the 2 coverage because they would be covered here, discussed here. If your G cow covers the lead of H, that's in this category. So here, this G leader will not cover the H leader. This H leader does not cover the G leader. So here, make sure, right, AFG, the coverage of the G leader will cover all the G cows. The H leader will cover all the H cows and no overlap here. So AFG would be on the left of the H leader, does not cover the H leader. Here, the coverage of the H leader does not cover the G leader. These 2, either way is fine. Make sure there is an overlap because here, right, G cows will come first. Here, the H cows will go first. So these 2 would be either or. If that's the case, we're also going to increase the count by 1. Okay, and then print answer that's correct. Okay, so here the key observation is a cow would never visit to the left. And then you can derive the 3 scenarios of the pairing of the 2 leaders. All right, okay, that is for the first one, not too bad. Actually, from the feedback we got from many students saying question 1 was actually on normal difficulty level. That is true. So just to be careful, don't have the overlap. No overcounting, or maybe you miss the like this one, right? A G can be any place on the left of the H leader, as long as this one covers the position of the H leader, then this could be also a leader. So read the question carefully and then no undercounting. Okay, that's question 1. Question 2, the error conditioning. For a lot of students saying this is the hardest one. It could be the hardest one actually, but once you realize it, it's actually not too bad. Okay, we're given n cows, n is only up to 20, and they stay in a barn that has 100 stalls from 1 to 100. Each cow occupies a range of the stalls, and then the stalls will be all distinct, no overlap. Range of the stalls by different cows are all disjoint. And each cow I must have the rooms, a range of the rooms, right, they cover. The temperature should go down by at least CI here. So that's the requirement. And how we can achieve this one, we have M machines, air conditioners. M is at most 10. And then each machine can work from the store from AI through BI inclusive. And each room, the temperature can be reduced by PI. And there is a cost. Cost is the MI here. Now we want to find out the minimum cost using some or all of the air conditioners so that all the cows' demand will be satisfied. So each cow eye, the temperature of those stores occupied the cow would reduce by at least CI. We can have all the machines running and put them in the spaces you want and see whether they can bring down the temperature, at least the CI for each cow eye. But maybe that's not the best one. We can use maybe just some of it to achieve the same effect. So since M is at most 10, we can enumerate all the possibilities. So this actually can be solved using a typical recursion. And we have done this to enumerate all the possibilities of using some of the M machines. So as we have done before, actually, we have provided a similar question to solve called group sum, giving you an array of integers, n of them, n is no more than 10, no more than 20. So can you pick some of them so that the sum is equal to a target t? So there we did a similar approach. So you're going to enumerate all the possible subsets of this array of size m. So if you want to enumerate all of them, so that's 2 to the power of n, including the empty subset. If you say a t is not 0, then you say 2 to the power of n minus 1, all the proper subsets. That's 2 to the power of n minus 1. Try all of them and see whether the sum is equal to t. If any subset, the sum is t, then you report true, otherwise report false. Okay, so here it's roughly the same. So we're going to find all the subsets of the M machines. So again, the possibilities will be 2 to the power of m and minus 1. Here, uppercase m, lowercase m would be the same thing like this one here. Since m is at most 10, so this one is actually less than 2 to the power of 10 minus 1, so that's 1023. So we can enumerate all these 1023 subsets of the machines and put all the machines working. So suppose this machine is chosen, right? It's chosen here. Each one we're going to, it has the range, right? Working from position AI through position BI. So each one we're going to see how much it will decrease the temperature for the stores from 1 through 100. So for each one, it will reduce the temperature for these stores, right? The second one maybe for these guys, for this one, maybe for this guys, and so on. So we're going to add the contribution of all the temperature reduction and add them together, get the total count for each store. What is the room, the temperature decrease, and compare this one for the CI. If the reduction is big than equal to CI, then this choice of the machines is good, and we're going to add the cost together. So this is actually a brute force approach. Since M is so small, we can't afford it. Okay, you can implement this subset using a bit mask, but for bronze, we think it's more appropriate to delay this discussion for bit masks. It is used widely for higher levels, but for bronze, we prefer to use recursion. And since we have covered questions of this type, not just once, group sum is a typical example. And for those who are familiar with our curriculum, we have another problem, the game score. So in the game, you play n rounds. Each round you have, say, m scores. So after playing n rounds, can you enumerate all the possible total score a team or a player can receive? So in that case, the same. You're going to enumerate all the possibilities and get the total score. So both questions can be solved using a recursion. So in this recursion, that's how you set this up. Let me clear this one here. So this is one typical way to do it. So we're going to start from, say, this position X, and we're going to keep track of the impact. So we have processed the machines. Remember, right? The machines would be at most 10. So we're going to go from 1, 2, 3, all the way through 10. Suppose we have processed machines from 1 through X minus 1. Some of them are picked. Some of them we did not pick. Remember, right? We always pick some of the machines, could be all of them. And for these guys, we have the contribution to the stores from 1 through 100. And we're going to keep track of the decrease of temperature in each room. So this will be saved in this stores array. Keep the impact of these. And now when it comes to the machine X, we have two choices. Either we're going to use this machine X or we don't use it. So if we don't use the machine X, then the stores will not change, right? Will still be the contribution from some of the machines from 1 through X minus 1 and keep it working forward. If we do pick machine X, then machine X will work and it will change the temperature from AX to BX, right? The stores, and we're going to increase the PI, the reduction, right, for the temperature. Add PI to those stores from AX to BX. So we're going to update this array stores and pass it on to the next position. So this is recursion, right? We go X from 1 all the way through M. M is the number of the machines we can use. So the base case would be when X is M, then we're going to check for all the temperature reduction in the stores 1 through 100. If for each one, the stores I is big than or the CI, then this is a valid choice of the machines. Remember, right? When we have reached the end, some of the machines are chosen, some of them may not be chosen. So for this configuration of the machines picked, we see whether the temperature in each room that has reduced at least CI degrees. If it is true, then we say that is a valid configuration of the machines, and we're going to add the cost. That would be easy, right? We just add all those machines that have been picked, add the cost together, and use this one to compare the minimum cost. If it is smaller, update the minimum cost. Otherwise, leave the record alone. So that's how you run the recursion. So the loop variable or the recursion variable would be X. Here, the base case actually is when X is equal to M, then we're going to stop. You don't call the recursion any further, right? So that's a very typical recursive function. Okay, so let's go through this recursion. So I'm going to still run this one. Here, since we're going to do the recursion, I don't want to pass too many variables, so I'm going to make these variables global. So n, number of the cows, m, number of the machines, make these global. Cows, so these would be the demand for each cow. I'm going to assign, keep this one in an array of size n by 3. N, that's number of the cows, so n rows, 3 columns. Column 0, that's the start of each cow's occupation. Column 1, that's the end. So start T in the here. So each cow we have the start store and then the end store TI. And also the minimum decrease over this interval from store S to store T here. So that's the CI, the minimum decrease of the temperature in the stores in this range inclusive. Any information for the machines will be saved in this array, also would be stored in this global variable machines, and has m rows and 4 columns. Column 0, that's the start coverage. Column 1, that's the end. So that's the A and B as specified here, from each A to each B, again, inclusive. And column 2, that's how much degree the temperature reduction or decrease would be over the interval from A to B. And also column 3 would be the cost. So for each machine, we have 4 quantities. So all saved in these 2 arrays, counts and machines. And the minimal cost, we're going to make it also global, since we're going to use it in the recursion. Initially, we're going to make it infinity, integer.max. Now we're going to have the stores. So remember the stores, we're going to keep it to record how much reduction or the decrease in each room or in each store. Initially, so far we have 0. So here, when this array is created, right, no machine has been pegged, so no reduction in each room. So we're not talking about, right, going down. Actually, we're going to say how much it has decreased. So we're going to keep a positive number, that is how much it has go down. And then we're going to call the function solve. The position x start from 0. Actually, it's 0 indexed rather than 1 indexed. That's the initial store decrease. And we're going to have the 0, that is the cost. So this one we do pass as a variable. All others we're going to keep, these values we're going to pass as variables as we run the recursion, and then the others we're going to keep them as global, because we don't want to change, we don't pass them around because they don't change. But the stores will change, the cost will change, and then the x will change. So we're going to pass these variables. When we're done, we're going to just print the minimum cost. So hopefully we'll, in this recursion, right, we'll update the minimum cost as it goes to the very end. The base case when x equals m, in this case, actually, if x is m, that means we have finished all the machines. You don't have to track anymore. So no further recursion here. So in this case, for the others, we're going to call the function itself recursion. All right, okay, let's take a look at the function here. So the purpose, having processed the machines from 0 through x minus 1, now, and also the incurring cost, right? How much cost by picking those, some of the machines in this range, the temperature decrease over each store is saved in stores. Okay, so all the variables, the meaning is clear. Now we're going to try, that's the base case. When x is m, that means we have gone through all the m machines and has gone to, because every time, right, we go recursion, we're going to try x plus 1. So when x was m minus 1 plus 1, that's m. So that means we have actually finished all the machines. Now let's see whether the temperature decrease or reduction, right, has satisfied all the demand from the n counts. Initially, we're going to say it is valid unless we say at least one store, the temperature reduction is not enough, then we're going to say that's invalid. 2 layers here for n counts. For each count's coverage, we're going to find out in this position, right, from the start to the end. P stands for the position in the stores. If the store's temperature deduction, if it's less than the demand of this cow J, then we say that's not good. So for this cow J, her demand has not been satisfied, then we're going to say this configuration of picking the machines is not good. We're going to return false. I mean, when we break this outer layer of the loop, we're going to see valid is false. So when we come out of the 2-layer loop, we say if valid is still true, then this is good. We're going to compare the cost with the minimum record, update it if necessary. Otherwise, you don't do anything. If it's invalid configuration, no matter how cost is, right, it's not going to change the, not affect the minimum cost record. And we're done. No more recursion. That's the base case. Otherwise, we're going to have two choices. Either machine X is not used, so it does not change the stores array. So we're going to move on to position X plus 1, or the machine X plus 1. Cost still has not changed, right? Because we did not pick machine X. So these two variables will stay unchanged. So recursion. And another scenario would be if machine X is indeed used. Okay, so if the machine is used, then it will affect the stores, the array. So now we're going to say, in the coverage of this machine X, start from the S here, ending with T. So for each position, the store, right, from S to T here, each store here, the temperature reduction should be increased by this PI. The reduction of this machine X here, which has been stored in column 2, how much temperature decrease would be if you use this machine X. All right, so now if we go to position X plus 1, we should have the new temperature reduction for each store, and also the cost, since this machine X has been chosen. So we need to add the cost to this one. So this is when we process to the next machine X plus 1, right? These are the new variables. And this one also would be recursive. Okay, so here, this is the step you may find a little bit surprising. So if we have picked machine X here, I need to restore or erase the impact of machine X, or can say restore the status before using the machine X. Remember, right? We have used this array stores just throughout the recursion. We did not copy. So here, for example, right, I have done, say, maybe going here at X here, and I have done gone recursively, and then maybe this is, say, N here, not M, or M minus 1. I did pick this one machine, or did pick this one here. Now, when I do X plus 1 here, I may have the choice not picking M minus 1, picking machine M. So I need to restore, right? When I start this one here, right, all these guys supposed to be not picked yet, because we have not seen these machines. So I need to restore the status. If you have added the contribution, right, so minus the contribution. Okay, so if the step is a little bit advanced, this is called actually the technical backtracking. If you don't want this one here, there is another easy way. So every time you call this X plus 1, make a copy of the machines, the stores variable, make it stores 2. So it will not affect the at X position X here. So every time you're going to make a copy, the storage is not a big deal. Why? Because N is at most 20. So either you create a variable of 1 integer, or create 20 variables, 20 integer variables. That's not a big deal at all. So maybe that is a better way. So when you try to do the recursion, just make a copy. So stores and new stores, here the same new stores. So if you do this back right, you don't have to backtrack or restore the status, because you have copied into a new one. You did not mess up the old array. Okay, so I think this is very similar for those who have taken the bronze class at Momentum Learning, and you can check my old lectures for the problem, for example, the group sum or the game score. You're going to see would be very similar to this question. Okay, for those who are doing the C++, I'll just walk through briefly, roughly the same idea. So N and M, number of cows, number of the machines, cows information, machines information, and a minimum cost. So this actually would be very similar to what we did in the Java code. So solve the same, the base case, assume this configuration is valid until we find a violation. The temperature decrease at store P is less than the cow J's demand, then we say that's invalid, and we're going to stop. And then at the end, when valid is still true, no violation, then this is a good configuration or picking up the machines so that every cow's demand has been satisfied. Then we're going to use it to compare with the minimum record. Otherwise, you don't. So that's the base case. The recursive call actually code is almost the same. Actually, it's not almost, it's identical. Nothing has changed. So if machine is not used, or if machine X is indeed used, and then you can, if it's used, you have to recover the status before using this machine X. Again, as I said, right, do not mess up the array stores, or you can copy a store so that you don't have recover. These are the same. So information of the cows here, the information of the machines. Initially, the temperature decrease is 0, and we're going to call this one recursive. At the end, print minimum cost, then we're done. Okay, so the code for both Java and C++ almost identical. Now, question 3, the move operations. Actually, for many students, we're happy to hear from them saying, okay, question 3 is indeed the easiest one. So many say, okay, we finished this one within 30 minutes. That is good. Actually, we do also hear some saying, okay, I spent too much time in question 2. So when finally I tried to take a look at question 3, I was running out of time. So that's also a lesson. You don't have to finish the questions in order. So maybe at the very beginning, right, maybe the first 10, 15 minutes, read all 3 questions and estimate which one is the easiest one. So start from the easiest one, because every question, no matter hard or easy, right, carries the same weight. So total cost score is 1,000. Each question actually covers weight 1,000 over 3. So for some, actually, the good strategy, work on question 3 first. You get this the full score for this question, and you can go back and work on question 1. That's another 333, and then you can take the second, try to work on the second question. And if you can think of the brute force, then probably you can get some of the credits. Oh, actually, that's not matter, since M is so small. It does not say maybe so many test cases. M is so small, right? Actually, this one just enumerate, does not make any difference. So whether you like it or not, right, for user questions, always start from the easiest one. So for this question, we are given Q words. Each word has the letters either M or O or uppercase. And for each one, we're going to work independently. See whether each one we can eventually reduce to MOO. The allowed operations are this. If you start from a string S, you can either work on the leading one or the last one. Either remove the first one or remove the last one, or change the leading one or change the last one. So change can also be, say, if it's O here, you want to change it to M. If this one is O, you want to change it to M. Well, of course, you don't want to change into M. But the first one, it's possible you're going to change to M, right? The last one, maybe you're going to go opposite, change from M to O to have MOO. So each time removal or change counts as one operation. And now we need to find out, report, what is the minimum number of operations so that we can reduce the string S into MOO move. Okay, since each one is independent, so we're going to read one string and process it, and then work on the next one. So you don't have to store the strings. Okay, so for many, this one actually, this is actually kind of straightforward. So initially, we're going to try if the string contains MOO as a substring. If you have this one here, then you write the length. I'm going to do say n minus 3. That's the number of the operations, because for all others, right, every time you just cross one or cross one, right? until you have just MO left. So the number of operations would be n minus 3. This is the minimum number of operations. Sometimes you may have to change, right? For example, here, MOM. You don't have MOO, but you can change the last M to O, so you can have MOO. So that's one operation. But for this one, if you already have MO, then you don't have to do anything, right? Then for this one, the answer is 0. Of course, sometimes you don't have an answer. For example, MMO, then you don't have a way to do it because you cannot remove anyone. If you remove it, then you don't have 3 letters. But you can only work on the first one or the last one. You cannot never have chance to work on the one in the middle. But here in the middle is M, so it's impossible. So whenever it's impossible, report -1. So first, we're going to check whether MOO is a substring of S. If it is, that's the answer. Life is beautiful if you have this one here. Now, if it's not, then you're going to take it a step back, right? Do we have MO? If I do have MO, then life is also not too bad. Why? Because if you have MO somewhere in the middle, right, I'm going to remove a lot of things from behind and then leave one last one. This must be M, right? If this one is O, then you know you have MO already. That's in the first scenario. So if you don't have MO, then you must have MO and M here. So I'm going to remove all the others here, remove all the others here. So the last step, you're going to change the M to O. So here you're going to have n minus 2 operations, right? You have the last 3 letters, so n minus 3, but this M, you have to change it. Here you don't, you just left with the 3, so that's n minus 2. Or if you don't have MOO, you may have OO here. If you do have MOO, then you're going to do roughly the same, opposite. So you're going to remove these guys until the last one here, right? The one right before this O must be an O. If you have an M here, then that's already MOO. So here you're going to do MOO to make this one. That's also n minus 2. The last scenario is you're going to have, you don't have MO, you don't have OO, you don't have MO, you do have NO in the middle. So you're going to end with, so somewhere you have, maybe you have M here. You have a lot of M's and M's here, and you have O here. That means we must have an O somewhere in the middle. We do have a scenario, right? I do have MOO, but this, either MO, right? So I have MO here, but MO is at the very end. So MO does appear, but appears as the very end. This actually does not help us, right? You have a lot of M's, or maybe you have an O at the beginning, but the MO occurs at the very end. So this one still does not work. So we want to find out between position 1 and position, so that's position 0, that's 1, that's n minus 2, that's n minus 1. So between position 1 and position n minus 2, there's at least one O. If you have only M's in the middle, then the answer is incorrect. I mean, it must be 1, right? Just like this one here. There is no middle, there is no O in the middle. Because you do need 2 O's, right? MOO. So this, you need an O in the middle. So if you don't have that one, then you can't. So we're going to see here, right? If you do have an O in the middle, so I don't know what you have here, what you have here. You must have an O in the middle. Then I can do this one, change this to O, change this to M. So that's n minus 1 operations. Actually, this would be kind of similar to what we have here. If we have OO, MO occurred at the very end, OO occurred at the very front. You do have OO here, but not like you have something here before, but you only have O as the first one. So you can change this one here, but you cannot change you have to change this M at the very beginning and then hope the nth gate, right? There is another O at the end. So in this case, you're going to do also n minus 1 here. This one has to change and this one has to change and this one cannot be another O. Of course, if this one you have an O, then you have OO occurring not at the very front. Okay, so the three cases, actually four, MOO and MO and OO, and you only have one O in the middle. If you don't have any O in the middle, then we're going to, otherwise, right? If you don't have anyone, then you have no O in the middle from position 1 to the end, right? We're going to say that's impossible to do it. So that's the answer n-3, perfect. N-2 for these two, you're going to just change one end, change two ends, n-1, and then if you cannot change anything, then the answer is -1. So the answers would be these cases. So we're going to just talk about these in order. So this will be a nested conditional statements. So let's go over here. And that's number of the queries. Oh, why don't we use Q? Is N specified in the question? No, actually Q. Let's change back to Q here. The number of queries, and then for each one, you can say this is N. So let's change. Okay, I'll just keep using N. So for each query, we're going to read the string S, and the length is stored in len here. Answer by default, it is -1. If the length is less than 3, we're going to say you cannot do it, right? So now if length is 3, I'll just do the simple one here. Whether it is, how much difference it is away from MOO. If S0 is not M, you have to change once. If the middle one is not O, change once. If the middle one, the last one is not O, you're going to change once. If the middle one is O, then that's the answer. If the middle one is not O, then the answer is -1. Okay, so you don't have to check the possibilities, right? Or just check the how many different locations differs from MOO. Okay, so that's when length is 3. Maybe you have some experience debugging when length is 3, or you say when length is bigger than equal to 3. So here, I'll just simply single out the case when length is 3. Then that will make life a little bit easier to write. Now we're going to talk about when length is bigger than 3. So it's handled here. We're going to find out whether S has MOO. If this MO is indeed a substring, then answer is easy. Would it be just length -3? Otherwise, you don't have MO, but you may find out MO here. If you do find MO, but MO is not only at the very end. So you do have MO and followed by some others, right? Must be MOM. Then we're going to remove everything before the first M and then change the M that after the O. So that would be length -2 operations to arrive MOO. Okay, I have removed the excluded the case, right? When MO occurs only once and only at the very end. If MO appears before, you have multiple copies. Okay, here, keep in mind, when I say the index of, actually this would be the first location of MO. If MO occurs only at the very end, you don't have any other MO here. That's the case, then you cannot do it. So here, if log1 is not negative and log1 is less than length -2, so this is length minus 1, that's length -2. So if this location of MO is less than n-2, then you know, right, MO is not the last 2 letters, are not the last 2 letters. There must be at least 1 letter after this O. So in that case, we can do it. We're going to remove everything before this M and change the last, this one to O. And if you have more else, right, remove all those. So that's, these 2 will be kept. The others we're going to change or remove. So that's n-2 here, number of operations. And if you don't have MO, but you do have, you're going to check for OO here. We're going to do the last occurrence of OO. If log 2 here is positive. So it's not the only one at the very front. If you only have a OO at the front, so here OO and you have M here, right? If you have OOO, then you'd have the occurrence of OO not just once. Okay, so here the last OO is not at 0. So this one is at 1, that's okay. So you have something in front of the first O we pick. But if you have O here, right, then you don't have anything to add to the front. So we're going to do this one. So here we're going to keep these two and then the others, right? After this one, we're going to remove. Before this one, we're going to remove and then change the O, this O right in front of the first O we pick, changes to M. So that's also length minus 2 operations. Now the last one is if you do have an O in the middle, actually this one actually will overlap with this. Okay, so we're going to have just in the middle, you have M here and M, or you have M here, that's fine. But if you have an O in the middle, we're going to keep position 1. So here we're going to do substring from 1 length minus 1. So this would be length minus n minus 2 here. In middle, if you do have an O, that would be great. I don't care about the others. If you have an O, we're going to remove all these guys. Remove all these guys, except right, you have M here and O here. So we're going to do length minus 1, keep just last O. If you have other scenarios, maybe this is not necessary. If you have MO, O in the middle, then has been covered in this MO here. Actually, you don't have to. Oh, could be, oh, it would be the MO, the double OO here. And a lot of M's here, then we're going to change. If you have an O, that's great. If you don't have, then also that's double O. Actually, this one is actually covered in these two cases. So you don't have to. Yeah, anyway, so these will cover all the cases. And if you cannot do anything by default, if this is not the case, this is not the case, not the case here, then the answer must be -1. That means the answer is by default here. You don't have to cover anymore, right? So at the end, we have covered all the cases, then the answer is print. So this one is actually the easiest one, at least for most students. It's straightforward. You don't have to worry about it. The complexity or the number of iterations you need to run, as we did see right in question 1. If n goes to 10.5, you may be scared. Or in question 2, if you are not so sure running all the subsets, that's also kind of scary. But for this one, most students can think about the way and run the different scenarios and find out the right answer. So for this past round, January 2023, we would say the difficulty level actually is at the average compared to season 2021, season 2022, season 2023 so far is actually better. That's also consistent from our feedback from students actually across the nation. Say actually season 2023 we feel much better. For some say we did get a promotion, even many got perfect scores, and some say not close, not promotion yet, but we are much more confident. So that's actually what we want to encourage you to do. So practice more, especially right before the contest, about a week or 10 days before the actual contest, warm up so that you can fine tune to the best status, so that you can do well in the contest. You can come up with the idea faster, and you can also write the code faster without a lot of mistakes. Debugging is a process can be frustrating. and the time consuming. So if you warm up many times, the bugs will not appear that often, and you can also find out the bugs faster than otherwise. So with this, I'll stop here and see you guys later.